Hello everyone, welcome to Computational Foundations of GIS, our second lecture. It's directly continuing from our previous lecture. It's actually the same set of slides. Second half I'm presenting today. And let me briefly summarize what I presented last week, or 2 weeks ago actually. So the big topic of the lecture was GIS in general, and in particular data modeling, where we were discussing how to develop object-oriented models of our world and how to implement such models then, for example, in a database. Well, and that's what I'm also going to address today. I'm talking more about the implementation than last week. So we will now focus on specific programming languages and database systems to implement such models we defined conceptually last week. Let me go quickly over the slides of last week. So we were discussing basics of geoinformation systems and GIS programs. Then we discussed raster and vector formats, the different geometry types that are there in use. We discussed also the difference between a field-based and object-based view of our world. Well, and then finally we ended up with data modeling in terms of objects, where we then had this stepwise process going from, well, rather abstract towards more concrete models. And in particular, we focused on this conceptual modeling, which we discussed with a certain example. So the conceptual model is actually the first time that we have something more formal than the results maybe of an interview with our users or our customers. So in the conceptual model, we have defined all relevant aspects in terms of classes, attributes, and associations. And the next step I will talk more about today is the logical model, where it's about implementing the conceptual model, for example, with a certain programming language or a certain database system. That usually means that we need to decide for data types, well, something like int, which is a data type available in most database systems and programming languages. It has a certain range, so it covers something like -2 to the power of 31 to 2 to the power of 31 minus 1. That is the range of integer numbers that can be represented with this data type int. This is quite typical in computer systems, that we have numbers with limited ranges and limited precision, whereas in the conceptual model we have basically mathematical definitions. We can say that, well, we are dealing with natural numbers, real numbers, or integer numbers in general. So that is the main difference. Also in this implementation, we are dealing with, well, table structures or class structures rather than having a conceptual definition of classes, attributes, and associations. We had this as a running example last week, so this nice pizza delivery service, Da Luigi, having different zones and customers and menus and so on. And with that we came to this conceptual model. We used UML, the Unified Modeling Language, to develop this class diagram showing 4 different classes with associations between them and the attributes of the classes. We also discussed special associations like, well, directed associations, aggregations, and compositions. And finally, this was the last slide I showed. Well, we have this conceptual model, and then now it's about implementing this model in a computer system, that can be, for example, a running program which reads some data, which internally organizes this data in a class structure, so the classes of a Java program, for example, and well, is doing something with the data, computing something, and writing some output. It could also be that we would like to have an implementation of our conceptual model in terms of a relational database where we have a persistent storage of our data. So it's somewhere on a hard disk of our server, for example. So it's not read and analyzed like in a running Java program, but it's stored in a persistent way on a database server. These could be two possible ways to go now, if we now develop a more concrete application of our conceptual model. And first of all, let me tell a few things concerning an implementation of our conceptual model as a Java program. That is something you did already in the exercise. Well, you were creating an Eclipse project, for example, and for each class, basically, you created a file, and the set of files was then your Java program, or rather the source code of your Java program. So if we choose this direction, we would like to implement this as a Java program, then for example, we have on the conceptual model side, we have these concepts like unlimited natural numbers. That is actually part of the UML standard, that we have these data types, unlimited natural, real, string. That is defined in the UML standard, and it corresponds very nicely to mathematical concepts like the set of natural numbers, the set of real numbers. So UML defines these data types in a mathematical way, or similar to these sets commonly used in mathematics. If we go now towards an implementation, then we have a data type int, as I said already, with limited range, a data type double with limited range and limited precision, so we cannot represent arbitrarily precise real numbers in a computer. Now, if you have something like pi, for example, then it's only a certain number of decimal points that can be represented. String is the same, it's just a sequence of characters. Each character, well, is somehow a defined alphabet, maybe 1 byte per character. That is quite common. Unicode could also be, well, quite common. So, and what I did now is actually also creating a UML diagram. So here, however, the UML diagram is not used anymore for conceptualizing. It is already much closer to the implementation. It's actually now writing these Java data types here, like int and string and so on. So that is the difference compared to the UML diagram you've seen before. Here I'm using data types as they are defined and available in the Java programming language. And also what is different here in this UML diagram, I have also methods. So I'm also showing which methods these classes have. And in Java, of course, we have like these instance methods, which we can call for any instance of our class order. Well, so we maybe also have a customer, and we have a method get house number. So we can take some concrete customer and ask him, please give me your house number. And that, just for reading these attributes, that is quite common to have these getter methods. And for writing these attributes, it's quite common to have these setter numbers. And then for creating new instances of our class, it's quite common to have constructors which have the same name as the class. So to create some object of type order, we would need to call this constructor method. That is quite common to have constructors, getters, setters, and then more interesting methods maybe like total price, which do some computation. So if I ask, okay, I have maybe some reference to one order made by some customer, I can ask, okay, please give me the total price for that order. Maybe I'm asking O.total price, and then this method computes the total price of that order. Of course, for that it needs to have the knowledge of the menu items which have been ordered. Yeah? And this knowledge is represented here in this array list. So there we have the menu items associated with that order stored in an array list. That is a data structure available in Java representing a dynamic array. So it's an array keeping an arbitrary number of elements in a given order, and dynamic means we can add new elements to this array list. So these are actually some attributes, or no, actually these are attributes implementing these associations we have seen earlier. So in the customer class, we have somehow an attribute with name zone of type zone. So, and with that, for every customer, we have the reference to the zone the customer is living in. Here, also we have the association from the order to the customer who made the order. So for every object of class order, we have the attribute with name customer whose value is of type customer. So meaning for every order, we store a reference to the customer who made that order. And then we have, we have the association between order and menu item. So for every order, we store an attribute of name menu items and of type array list. Well, actually, this is not just any array list, but it's actually an array list to keep objects of type menu item. That is what you can see here in these brackets. So the type of our menu items attribute is array list menu item, meaning it's an array list to store menu items. And that means just for every order made by some customer, we store an array list of type menu item to keep the information about which menu items were ordered with that order. Then we have these constructors, as I mentioned already. Well, they exist, of course, in every class, not just in the order class, but for space reasons, the constructor is given here only for the order class. And the constructor in a Java class is responsible only for creating this instance, namely to make a new order and to set these attribute values of the new instance. And accordingly, this constructor, it requires 3 arguments to be specified, namely somehow an int, well, that will become the identifier of our order object. Then some customer, well, that is the customer who made this new order. And some array list with all the menu items that were ordered by our customer. Well, and this constructor then simply instantiates our new order object and sets these attributes. Well, then we have these getters and setters as shown here, getting for reading, setting for writing. And finally, some other methods, as I mentioned, to make some interesting computations, more complex things, may be doing some calculations based on the attribute values. You may think of a class disk, for example, and a method compute area or something which can compute the area of a disk object based on its radius or something like that. Yeah? But here it's the total price for our order class computed based on the menu items in our menu items list. So this UML diagram in showing our model in Java. So actually there are some tools which can even create the Java program automatically from such a UML diagram. Of course, such a thing would not be able to implement this method here, like total price. There we need to specify our own implementation. But if you have such a UML diagram, maybe drawn with some nice tool, and then this tool can automatically create the Java code, meaning the 4 classes with the attributes, the getter and setter methods. But of course, a thing like this, a method that does some interesting computation, that we need to implement ourselves, because how should this automatic procedure know how to implement such a method? So that would be our task. Well, let's look at these classes. For example, the class zone. Well, you see in Java, we have here the name of the class. So it's a public class, meaning a class that could be used by any other class. So we have access to this. There's no limited access. This class zone begins with this curly bracket, and somewhere down there you will see the end of the curly bracket, and that ends the class. And this class zone, this code which you can see here, that would be stored in a file with name zone.java. Well, and you can see first of all here the attributes. So we have 3 attributes, each of type int, meaning it's an integer number. And here you see the attribute names. So a zone has an ID, then we have this min amount which needs to be ordered, and the delivery cost which is charged for delivering into that zone. These attributes here are set private. That is usually a good idea in Java to set these attributes as private, meaning no one is able to read or write these attributes except via these getters. So with this getter method, we make it possible to access these attributes, but actually by implementing these getter methods, we can control the way this access works. So it's not possible to do something wrong here, because with these getter methods or setter methods, we control the way these attributes are read or written. But let's first talk about the constructor, which is this method here. This method needs to be called to create a new zone. So we have public. That is here a good idea for our constructor, meaning anyone would be able to create new zone objects by calling this constructor, because it's visible, it's publicly visible. When creating a zone object, we need to specify these three arguments, the ID, the min amount, and the delivery cost. And this constructor does nothing else than setting the attribute values of our new object according to these three arguments, which are passed over to the constructor. So a constructor also does not return anything. It just instantiates a new object of our class. And, well, calling such a constructor could be done like this. So in some other class, we would have zone z is equal to new zone, and then these three arguments, maybe something like this. And not to forget, finally, the semicolon. It doesn't fit anymore on my whiteboard. That should all be written in one line of code. So that could be somewhere in your program. You create a new object of type zone, which we refer to as small z. By calling the constructor, constructor calls are always coming together with this keyword new. That gives you also the idea that there's really something created, which is now represented in memory of your computer. So we allocate some memory with this for that object with these attributes. The constructor is invoked, meaning we have then accordingly set the attributes of our new zone object. Well, we have these getter and setter methods. So for example, then after creating a zone object, we could write int my ID is equal to z.getID. With that, we would call this getID method. And we would accordingly read the ID from our object z and store it now temporarily in our variable myID. We could also say z.setID 100 maybe, so that writes the ID of our object z. I don't know whether that's a good idea actually. I would assume that maybe these IDs of objects, they are final. So if they are created once, we should not be allowed to override them. But here in this simple implementation, in this basic implementation, that's actually possible, because we provide this setID method. The same we have with this min amount and this delivery cost attribute. There we simply have a getter method and a setter method, which allows us to read and write these attributes. Well, let's look at the next class. That is our class customer. Again, it's public class customer. Then we have the attributes int ID. Again, our customer has an identifier. Then we have three attributes of type string. They are written here in only one line of code to save some space. First name, last name, address. Also, we have two attributes of type int postcode and house number. And one attribute of type zone that is written like that. So that is kind of special here because this type zone, that's our own type which we introduced with the class zone. So that is of course not standard Java code here. It is our own class zone. And because we introduced this class zone, we can also introduce an attribute of type zone. So with every customer, we store a reference to some object of our class zone. Well, the rest here is not very interesting because that's precisely the same as before. We have the constructor allowing us to instantiate new objects of type customer. Again, for each attribute we have one argument here. Maybe the only special thing is that we also allow an argument of type zone here. But basically all what we do is that we set the attributes of the new customer object according to these arguments which we pass over to the constructor. And with this dot zone equal to zone, we also set the zone attribute of our object according to the argument zone that we receive here with the method call. The getters and setters for this class are just implemented similarly to our implementation we have here. Well, then we have the order class. We have again public class order. Here, before writing this public class order, we have a set or a number of imports, so some Java classes which we will use in our code that needs to be imported before starting this class. So public class order, then curly brackets to indicate this is now the body of our class, starting here and ending here. Again, we have then our attributes, private int ID, private customer, customer. And now what is special here is that we say we have this attribute. Menu items is the name of the attribute, and the type of this attribute is array list of type menu item. That's how to read this. So it's array list of type menu item, meaning it's an array list which can keep objects of type menu item. And we have then this constructor. It's not shown on this slide. This is just, again, setting the attributes according to the arguments we receive with our method. And then we have now the most interesting part. Well, of course, we would also have the getters and setters for this class. But the most interesting part is now this method total price, because this actually does some computation other than just returning an attribute value. So this method, what it does is simply you have some integer number which we call st, so that will be our total price in the end. We initialize this variable with 0, and now what we do is we iterate over all menu items associated with this order. Namely, we have this array list of name menu items, and we say for each menu item m in the array list menu items, do the following, and the following means do everything within these curly brackets. And what we do is simply that we take the price of our current menu item m and we add that to our variable st. So this st plus equal, well, that is nothing else than, well, if you have something like st plus equal to, that is the same as st equal to st plus 2. So meaning st is incremented by an amount of 2. That is shorthand for that. So we read the value from st, we add 2 to it, and the result is assigned in the variable st. So this is, of course, an assignment. This equation symbol in Java represents the assignment operator. And after we have iterated all the menu items in our array list, we must not forget that we are also required to pay this delivery cost associated with our zone. So we need to ask the customer, please give us the zone you are living in, and that zone we need to ask, please give me your delivery cost. Yeah, so here with that dot actually we have customer, please give me your zone. And here we have zone, please give me the associated delivery cost. And this delivery cost then is added to this variable st. So in total, what we have here is the price for the order, including the price for all menus we have ordered and the delivery cost for our order. And this is then the result of our method, which we have here, where we return the result. The class menu item has nothing special, actually. It is just public class menu item, attributes as we had it before, a constructor, and a set of getters and setters for reading and writing our attributes. And that's all. We just need finally somehow an example to show you how to use these classes now. Well, we have now these 4 classes, namely zone, menu item, customer, and order. And now what I'm showing is an example code to make use of these classes. And actually for that I need another class which I call main. I could also just call it test maybe for showing you that this is a test class just for testing purposes. I have this public static void main method that is existing in every Java program, and it's the method that is executed when the program is run. So when the program is launched, this method is invoked. And now we go through these commands from top to bottom in sequence. What I'm doing is I create some zone objects, then I create some menu item objects, then I create some customer objects, I create some order objects, and finally I write something to the standard output, namely some information read from the classes and some computations, some results of my computations. Well, let's go through this code that is all now within these curly brackets you need to imagine within this body of our main method. So when we run the program, this code is executed. And the first three, actually this is one line of code. It's only one command with this semicolon here. So we have an array of type zone. This is now a static array. It's not this kind of array list where you can add new objects on demand. So this is a standard array in Java with these brackets. So meaning we instantiate this array. We do it here with 3 objects, and we cannot increase the size of that array. So this has a fixed size. However, what we do, we create one zone with ID 1. The first one argument here, that was the min amount and the delivery cost. So here we call the constructor to create a new zone object. Then we create here a second new zone object and a third new zone object. And these 3 zone objects are put into one array with these curly brackets. Here they have the meaning of showing the bounds of my array. And this array is then referred to as Z in the following. The same I do with these 4 menu items. Well, it's again an array, a standard array of type menu item, a standard array to keep menu item objects. I'm creating these objects here with the constructor of the class menu item, which requires 3 arguments, namely 2 numbers. The first is the ID, the second is the price, and the third is the name, pizza fungi, for example. And that I do 4 times for 4 different menu items, which I keep then in my array M, which is shown here with these curly brackets showing the begin and the end of my array. Then I have an array of type customer. Here I do the same. I put into this array, well, 1, 2, 3 different customers, namely Paul Klee, Karl Benz, Tina Turner. Each of them has an ID, namely 10, 11, and 12, respectively. Each of them has an address, Schlossstraße, Am Dom, and Hauptstraße. Each of them has a house number, a postal code number, and a zone. And the zone now is somehow interesting here, because to pass over a zone object to this constructor, I'm using the zones I have introduced beforehand, namely here. And with Z0, I'm referring to the first zone in my array Z. And with Z1, I'm referring to the second zone in my array Z. So keep in mind that in Java, this index of an array always begins with 0. Yeah, so Z0 is the first object in my zone Z. So it's that zone here, which I have specified first. And Z1 is the second zone in my array Z, so that is this zone, which I have specified second. Well, so this is now initially my zones, my menu items, my customers. Now I still need maybe some orders. My customers should also make some orders. And because these orders, orders I can create with the constructor of the class order. And this constructor requires the ID of the order, it requires a customer object, and it requires an array list of type menu item. And these array lists I first need to create. So there I have, for example, here this array list of type menu item, which I refer to as MO1. That is the variable name I'm using. I'm just creating this array list with the standard constructor. So I have this these round brackets opening and closing without any argument, meaning now I create an empty array list of type menu item. But I can then add to my array list 2 of these menu items I have created before. Well, that's my standard array M, and I'm using the second element from that array that was actually pizza calzone. So here I'm adding to this array list MO1, I'm adding pizza calzone twice, first time and second time. And then I have an array list MO2, which I also instantiate as an empty list. And to that array list afterwards, after creation, I add M0, which is pizza fungi. And finally, I create this third array list, MO3, and I instantiate that as an empty array list, and I add M2. So that was Insalata Mista. So now I have created these array lists, and with these I can now call the constructor of my order class. So I have order ID, customer, and the menu items nicely wrapped in an array list. So now I have created one order with twice pizza calzone, one order with 1 pizza fungi, and one order with 1 insalata mista. That is now actually the same. we have seen earlier in my example, I think. And what I can do then is I simply, what I want is actually for my first order, namely that is the one here at index 0 of my array O. Yeah, I'm asking array O at index position 0. That is the first order in my order array. From that, I get the customer and the last name. That I write to standard output using this print line method. So this print line method, it writes some string to standard output, and I'm doing here something like get the customer name of my order at index position 0. That is written to standard output. However, I not only write this customer name, I also write this colon, and I write the total price of my order. And that I do by calling this method total price for my order object at index position 0 of my array O. Well, and this total price, what is that actually? It should be twice the price for pizza calzone plus the price for delivery to the zone of customer Klee. And if we look here, pizza calzone has a price of 12 euro, and Paul Klee lives in zone number 1 with 3 euro delivery cost. So it's 12 plus 12 plus 3, which is precisely what I see as output, namely this 27 euro. That is the price, the total price of my order, namely this one. Well, so that is now a nice Java program. It simply creates some data, and it then analyzes this data using this total price method. It computes the total price of our order. That's it. It's a really fast crash course in Java, I should say. Of course, you will do much more in the exercise about this. But I think this nicely shows how you get from a conceptual model to an implementation in Java. It's almost automatical that you create for each class of your UML diagram a Java class. And for each attribute of in your UML diagram, you create one attribute in the Java class. Well, in Java, you usually have these constructors and getter and setter methods, maybe some additional methods to do some interesting calculation. But that is actually the logical model then, that you are dealing with these data types available in Java. So I hope that, well, this was too fast probably for getting an understanding of Java, but I hope it was clear that we can get quite straightforward often from a conceptual model to an implementation in Java or in any other object-oriented programming language. I could have done the same with C++ maybe, or Python or something. So that is then a Java program or some computer program which you can run, which you can execute. It reads data or creates some instances, and it does some calculation. This is often not what we want. Sometimes we also have in mind to create a database where we keep data according to our model in a persistent way. So for persistent storage of data, databases are good, and these databases also can be implemented according to a conceptual model defined, for example, in UML. And that's what I'm going to show next. So I use the same conceptual model, but now I'm not implementing it in Java as an object-oriented program, but instead I'm implementing a database. And well, I'm using a relational database here. In the exercise, you will use maybe PostGIS. That is what we use quite frequently in my geoinformation group, PostGIS. And it is also quite straightforward to get from the conceptual model, where we had these 4 classes, to a database structure. And again, what I am showing here is that what we can do basically is, for every class of our UML diagram, we create one table. That is the most important approach from the conceptual model to the logical model. But that is not working in all cases, and I will show you why. So here I did this simply, first of all, that I created for every class of our conceptual model, of our UML diagram, I created 4 tables. And if you think of relational databases, actually this term relation in relational database means nothing else than tables. So in that terminology, a relation is just the same as a table. The idea is that it relates multiple values with each other, because you have in one row you have multiple values. Therefore, a table in the context of relational databases is the same as a relation. And here we have one table per class and one column per attribute. And additionally, we have these columns representing associations. If you think again of our UML diagram, I'm going back in my presentation. That was our UML diagram. There we had associations, for example, from customers to zones and from orders to customers, so that we know for every order who was the customer who made that order. Yeah? And that is exactly what we have in the table structure. Here we have, well, in yellow you see the identifiers of the customers and the zones. And these associations in this table structure are simply implemented using an additional column, keeping the key or the identifier of these rows in the other table. And that is called actually, well, sorry, that is called foreign key, meaning it's a column containing a number or some value representing the key of some other table. So every table has a key which allows you to uniquely identify the different rows. And these associations are simply implemented by having the key of some other table here in this column. And that is actually in yellow. That column is also called the primary key of a table. And this pink column here is called the foreign key, because it refers to a column of some other table containing the primary key. So you see that order 13011 was made by customer 10, by Paul Klee. You see that order 13012 was made by customer number 11, namely by Carl Benz, and so on. You see that Paul Klee lives in the zone with ID 1, and thereby you also have the information that for that customer, whenever he makes an order, a minimum amount of 10 euros needs to be ordered, and the delivery cost of 3 euros is charged. So that works nicely. However, what does not work here, we also had this association between the menu items table and the orders table that we cannot represent using just a extra column, let's say in the menu items table or in the orders table. So that would not work. We could not represent this association between menu items and orders using a single column. And the reason why this doesn't work is because this association was of type many to many. I'm going back in my slides again. Here, between the menu item and the order class, we have this many to many association. Every order can be ordered, every order can contain an arbitrary number of menu items. And on the other hand, every menu item can be contained in an arbitrary number of orders. And that is called a many-to-many association. Well, we may think of a solution as follows. Well, we have the orders and the menu items. I'm showing that on the whiteboard in a minute. We may think of the order table or the orders table. That is how I have shown it on my slide, with two columns. So every order has an ID and a customer ID. That is what you can see here. And now we may have the idea to introduce an additional column. Maybe we have order 1, customer ID 4, order 2, customer ID 3. And now we could have the idea to keep in this menu items column maybe all the menu items that were ordered in that order. For example, like this. That would be an idea. Thereby, order 1 would have contained these 3 menu items. Order 2 would have contained these 3 menu items. So that could be an idea to get along with just an extra column in our orders table. But this is something that you should forget, because in relational databases, these columns, they should be, or they should contain values that are atomic. So we need to contain atomic values like 2 maybe, or 4, but not a list 2, 3, 4. A list of multiple numbers would not be atomic in that sense. So the reason why this is not allowed is that in relational databases we have queries, and these queries are optimized only for atomic values in these columns. And that is the reason why introducing just one extra column to represent our many-to-many association does not work. We need some other idea, and basically the idea is to represent this association, this many-to-many association, with some extra table. We introduce one table just to represent our association. So we need a new table just to represent our association, and this new table will consist of columns with atomic values. So that is important here. Many-to-many associations in relational databases, they are represented with extra tables. And now we can see by having this extra table, well, we have this extra table also has a primary key to make every row distinguishable from every other row. And then we have these columns, order ID, menu item ID 2. So you see, if you look at all the rows with order ID 13011, you see that there are there's twice this value 2. So the order with ID 13011 is associated twice with pizza calzone. So in other words, someone here ordered 2 of these pizzas. And that is represented now in this table. How many menu items and which were ordered in each order. So that is now a full implementation of our conceptual model in terms of a relational database using these 5 tables. And again, in yellow, we see the primary key of each table, allowing us to identify each row. And in pink, you see these foreign keys, which are actually references to primary keys of other tables. Well, that is how to get from a conceptual model to a database structure or a structure of a relational database. So I would like to talk now a bit more about databases. Well, what is that actually? What is a database? And maybe you are more familiar with working with files, with file-based systems. If you think of geographic information systems, it's quite common to work with shape files, for example. Yeah, and also shape files usually come together with these DBF files, which store attributes of tables. So you may think of a file-based system where you have multiple files, each representing one class of objects. So the problem with such file-based systems is maybe you manipulate one file without looking at the other files. And that can cause problems. That can easily lead to a loss of logical integrity, which means that the content of your data is not consistent with the data model. So as an example, we may have the situation that in this table here, we have maybe some number which should be actually a reference to a row of some other table. So this is the foreign key maybe referring to the primary key of some other table. And it can easily happen if you keep these files independent of each other, that maybe you delete one row from the shop table and then the reference is lost. So we have maybe some number here which should point actually to some row in this table, but such a row does not exist anymore because maybe some other user deleted the corresponding row. And that would be a loss of logical integrity. So we have a constraint violation, namely this foreign key, of course, has to point somewhere, namely to a row which has the same number as primary key. This can easily happen if you keep these tables independently of each other in separate files. And especially this can happen quite fast or quickly if you have multiple users working on this set of tables at the same time. So that is not a good idea to keep these in different files. Maybe some of these users is working on the article table, another one on the customer table. They don't know each other, they don't know of their different changes, and soon you will have a loss of logical integrity. So a better approach is therefore to keep all these tables in a database, which can be thought of a big container, and actually these users, they can interact with this data only via a so-called database management system. So this is a system which takes care of all the transactions made by the different users. Especially it will optimize the queries that these users make to the database, and especially if any changes are committed to the database, it will make sure that the logical integrity, meaning a set of constraints, is still satisfied before making any commit to the database. Any change, the database management system will check whether this change will cause any constraint violations. And that is nice because we always can be sure that we have logical integrity, logical consistency ensured by this data content. In the German language, we have a nice word for databases. The German word for databases is Datenbank, which literally translates to data bank. And I think this is a very nice image, simply, that you think of this database as a bank. First of all, because, well, the bank is somehow a safe place for your money, of course. A database, therefore, is a safe place for your data. But I think the idea of a database is also nice because if you go to a bank to make some transaction to your savings account, for example, for sure you do not walk directly into the safe room. Yeah? Instead, you go to the counter and you ask the assistant, well, maybe you want to withdraw some money or something. Yeah? Well, nowadays you rarely talk to these people working at the bank, but well, in these older times, former times, people actually talked to people at the bank. They talked to people at the counter and wanted to withdraw some money. And that is similar here. Well, we first need to go to this database management system, talk to that before we can make any change. We don't walk directly to the data and make any changes there because that would be very chaotic and result in a mess. So that is prevented with this idea. Well, so much concerning databases in general, and the remaining time of today's lecture, I would like to show you how to make use of data that is in a database, namely by executing queries to it. Queries with SQL. SQL is the most common query language for relational databases. Sometimes it's also pronounced SQL, so it's structured query language. And with that we can answer questions such as, which customers live in the street whose name is Schlossallee? Well, such a basic SQL query looks like that. We always have these keywords, select from where. And basically what we can do is, after the select, we say we would like to select all columns that we specify with this asterisk, with this star symbol. From, then we have the table name, customers, where, and now we have, let's say, a filter which allows us to filter out the information we are interested in. Namely, we are interested only in the customers living in Schlossallee, the customers whose address is Schlossallee. So we require that the address column contains the value Schlossallee. Only then we report the entries, meaning all columns of the corresponding rows. All columns of the rows where the address is Schlossallee. And as a result, if we think of these, let's see, this table here, we would actually get only one line as output, namely Paul Klee. So the result of such an SQL query would again be a table. Which meals cost at least 10 euro? That is also quite straightforward. Again, we use the same structure, select from where, and here after this where we have, oh no, sorry, I actually, if I'm writing these queries, I usually first of all think about which tables actually contain the information I need. That is the first question I ask myself, the first task I do. So I need to look at this question here, and of course, to answer that question, I need this menu items table. So that is what I write first. Select from menu items, where. Then I need to think of what actually do I want to return as output. Let's say I'm interested in all columns from the table. So I'm selecting all columns from the menu items table, but I restrict the solution, meaning the set of rows, the set of entries, to those rows where the price is greater or equal 10 euro. And that is precisely what I do here. After the where, I have this filter, or let's say the condition, specifying which rows I'm going to output. Return one of the most expensive meals. That is a bit more tricky now, but still it fits in one line of code actually. I have something like select all from table menu items, and now I'm saying, well, actually I'm interested of all rows first of all, but those rows I would like to order in descending order by price. So meaning the most expensive menu item will be first, and then the price is decreasing if I go down my result table. And finally, what I'm doing here, I say I limit the solution to the first row. Only the first row is shown and given as output. And accordingly, I will get one of the most expensive meals. Which of the most expensive meals I get, that is not stated here. It could be any, depending on, well, which meal occurs first in this sorted table. The sorted table sorted here in descending order by price. But for sure, I will get one of the most expensive meals. Well, let's go further. More SQL queries like this. Return the highest price among all meals. Well, I could do it very similarly. Instead of just selecting all columns, I could just maybe select the price. And of course, that would return the highest price. So if I would say select price from menu items, order by price, descending limit 1, that would give me the highest price among all meals. But I can state these queries also differently. There are always multiple options, or most often there are multiple options to state a query. And the most simple way to state this query or this question is using an aggregate function. So what I do here, instead of selecting multiple rows, I'm simply saying from this table menu items, I'm interested in this price column, and from that I would like to select only the maximum value. So, and that will give me the highest price among all meals. Well, these aggregate functions, of course, there exist quite many, like computing the average from all values in a column, or the total number of values in a column, the first or the last value in a column, the maximum and minimum value, well, maximum is what I used here, or the sum of all values in a column. So that can be used in queries like this. Furthermore, this is now getting a bit more tricky. For each meal, that has ever been ordered, return the ID of the first order in which that meal occurs. Well, for each meal that has ever been ordered, return the ID of the first order in which that meal occurs. Meaning the first order, meaning the one with the smallest ID. And that is what I'm doing here. First of all, again, I'm thinking of, which tables do I need actually to solve that problem? I need this table order elements. I would like to select menu item ID and the minimum order ID, namely the smallest order ID in which this order element occurred. But then what I need to do is also that I need to group by the menu item ID. So the order elements that has, the menu item ID and the order ID, but I would like to, let's see, I would like to group by menu item ID. I'm going back in my slides. Here. I'd like to group, first of all, by menu item ID, meaning I have 3 different groups, 2, 1, and 3. And from each group, or for each group, I compute the minimum of the order ID, namely 13011, 13012, and 13003. So, and that would be the result. I would have then 3 rows as output, namely 2, 1, and 3 in the menu item column. That is what I used for grouping. And the order ID, as it's written here, 13011, 13012, and 13013. And that is actually using this group by. So I group by menu item ID. Then I consider each group separately from the other groups. Within each group, I compute the minimum of that column, and that is what I then write. For each group, I have a pair, namely the menu item ID and the minimum of the order ID. And that precisely answers the question I've stated earlier. Well, return all the most expensive meals. So plenty of examples are possible, and especially what we can see here is that we can also use nested queries. So we have this query here we had before actually. It computes the maximum price among all menu items. And then I'm asking from my menu items table, I'm asking which are the menu items where the price is equal to this maximum. And according to my example I've shown earlier, well, you can see that pizza calzone and pizza tonno, they both cost 12 euros, so both of them have the maximum price, and that would be the result for my query here. Well, there are many more examples possible, and you can see that this was, of course, a very quick, I would say it was more a refreshing of SQL and some programming. This was hopefully raising your awareness of how important these things are. We are in the master's program, Geodetic Engineering. I'm assuming that you all have GIS experiences and from your bachelor's program, and you perhaps had contact already with SQL and some basic programming at least. Maybe not Java, but some other higher language. So that is required, and I think with this lecture today I've shown you like the level I'm expecting here. This is not a lesson well, from scratch. This is more like a refresher of things about SQL and basics about object-oriented modeling and programming. If you feel that this was too fast, then it's, well, more time for you actually to go through these examples very slowly, step by step, so that you are on the level that now we can continue. And actually in the next sessions, I will teach more about GIS concepts actually. There's much more to tell, especially in the context of databases. Of course, we would like to work with spatial data next. Yeah? So here, this was completely without any spatial information, without any geometry, and no coordinates involved. And what I will teach now in the following is also how to work with spatial databases, for example, also in conjunction with GIS programs such as QGIS. The next lecture, of course, will be online then in 2 weeks. That gives you time also to maybe fill gaps that you encountered when watching this video. And I just thank you for your attendance, for watching, and bye-bye. See you in 2 weeks.